In Module 6, we will discuss factoring polynomials. In Module 6, Section 1, our focus will be the greatest common factor. To start, let's look at a few definitions. The greatest common factor is the largest quantity that is a factor of all the integers or polynomials involved. This is the process for finding the greatest common factor, which is sometimes referred to as the GCF, of a list of integers or terms. First, we write each number or polynomial as a product of prime factors. That's called the prime factorization. We covered that in Module 1. Second, we identify common prime factors. And then third, we take the product, we multiply all of the common prime factors together. And if there are none, we say the GCF is 1. Let's try a few examples. Now, the first example, I will go ahead and make a factor tree just to remind you of how to find the prime factorization. After that, I will go straight to the prime factorizations of each number. So we start by trying to find the GCF of 12 and 8. Let's look at the factor trees. So remember, we try to divide 12 by any prime number that we can. 2, 3, 5, 7, so on. So we start with 2. 12 divided by 2 is 6. 2 is a prime number. 6 divided by 2 is 3, and 2 and 3 are both prime numbers. So the prime factorization of 12, we would say, is 2 times 2 times 3. Let's do the same thing with 8. 8 divided by 2 is 4. 2 is prime. 4 divided by 2 is 2. And 2 again is prime both times. So the prime factorization of 8 is 2 times 2 times 2. Once we look at the prime factorizations, we look to see what factors each number has in common. They have one factor of 2's in common, and they also have another factor of 2's in common. So we take each factor of 2 that 12 and 8 have in common, and we multiply those together to find the GCF. So the GCF in this case would be 2 times 2, or 4. Let's try the same thing with the next example. Again, you can make factor trees with each of these numbers. I'm going to skip that step because you should know how to do that by now. So starting with 7, 7 is a prime number, so 7 is its own prime factorization. So we just say 7 equals 7. 20, we can break that down to be 2 times 2 times 5, again using a factor tree. When we look at each list of factors, each product of prime factors, they have no factors in common. So with 20 and 7, we would say the GCF is 1 because they have nothing in common. Let's try an example where we have 3 numbers instead of 2. We do the exact same thing. So we start by finding the prime factorization of 6, 8, and 46. 6 can be rewritten as 2 times 3. 8 can be rewritten as 2 times 2 times 2. And 46 can be rewritten as 2 times 23. So looking at each list of factors, each of those numbers has a factor of 2, so they have a 2 in common, but that's it. So the GCF here is just 2. Let's try the next example where we have a few larger numbers. We have 144, 256, and 300. So starting with 144, it's 12 times 12, and if you continue to break the 12s down, we would have 2 times 2 times 2 times 2 times 3 times 3. 256 is going to be the product of 8 2's. And 300, we will have 2 times 2 times 3 times 5 times 5. So 2 times 2 times 3 times 5 times 5. So now we have the list of factors, the prime factorization, of each of these numbers. We want to see what factors they have in common. Well, looking at each list, we have a common factor of 2. We have another common factor of 2. And while 2 of the prime factorizations contain a 3, we can't say they have a 3 in common because not each prime factorization contains 3. So again, the GCF will be 2 times 2, which is 4. Let's now find the GCF of variable terms. We start with x cubed times x to the 7th. Remember that the exponent represents repeated multiplication, so we can rewrite x cubed as x times x times x. We can do the same thing with x to the 7th, but in this case we will have 7 factors of x. Now we look at common factors where they have an x in common, another x in common, and a third x in common. So our GCF will be x times x times x, or just x cubed. Now in the case of number 2, where we have a numerical coefficient and variables, we start by finding the GCF of the numbers, and we find the GCF of the variables, and we multiply those two together. So starting with 6 and 4, 6 equals 2 times 3. That's its prime factorization. 4 equals 2 times 2. So we see that 6 and 4 have a common factor of 2. Let's do the same thing with x to the 5th and x cubed. X to the 5th, we write 5 factors of x. X cubed, we write 3 factors of x. So we see they have 1, 2, 3 factors of x in common. So if we take all of the circled factors, multiply those together, the GCF will be 2 times x times x times x, or 2x cubed. Here we have another example where we have 2 variables in each term. So let's find the GCF of the following: a cubed b squared, a squared b to the 5th, and a to the 4th b to the 7th. We do this the exact same way. We expand using the exponents. So a cubed b squared, we have 3 factors of a and 2 factors of b. A squared b to the 5th, we have 2 factors of a and 5 factors of b. And last, a to the 4th, b to the 7th, we have 4 factors of a and 7 factors of b. There is a shortcut to this method, thankfully, because otherwise you can see how it takes a very long time to write all of these factors. But in this case, since we've already written the factors out, let's look at the common factors. I have a common factor of a. I have another common factor of a. That's all the a's we have in common. We then have a common factor of b, another common factor of b, and that's it. So the GCF will be a times b times b, or a squared b squared. Now at this point we can look at our answer and notice that a squared matched the smallest exponent of a that each variable had in common. And b squared matched the smallest variable of b that each variable had in common. And so when we're trying to find the GCF with variables, as long as the variable shows up in each term, you want to find the smallest exponent, and that will represent your greatest common factor. And that's exactly what this slide says. So you could pause it and study over this note if you needed to. Now we want to factor the GCF from a polynomial. This is always the first step with any factoring method. So we start by writing the GCF as a product, writing the polynomial with the GCF as one factor, the resulting polynomial as the other factor, and we will determine how to find the resulting polynomial in just a moment. So let's factor out the GCF in the following polynomial: 6x cubed minus 9x squared plus 12x. First, we just ignore the plus and minus signs that attach the terms, and we find the GCF of 6x cubed, 9x squared, and 12x. So to start, I write the prime factorizations of my numbers, of my coefficients. 6 is 2 times 3, 9 is 3 times 3, and 12 is 2 times 2 times 3. However, with the 6, we had an x cubed. Now, instead of writing out the x 3 times for the 6x cubed and 2 times for the x squared and once for the x, let's use our shortcut once we find the GCF of the numerical coefficient. So when we look at the factors of 6, 9, and 12, they have a 3 in common, but that's it. So our GCF is 3 times, now we have to go back to the variable. With the variables, we have an exponent of 3, 2, and then 1. So the smallest exponent is 1, and our GCF will be 3x. Once we find the GCF, this is how we rewrite the polynomial. We write the GCF on the outside, and then we're going to take every term inside the polynomial and divide it by the GCF. That will give us the resulting polynomial. Basically, when we factor out a term, we have to divide every piece by that factor to get the resulting polynomial. So this becomes 6x cubed over 3x minus 9x squared over 3x plus 12x over 3x. And as you do more and more examples, you'll be really good at doing this in your head. We go down to the next step, and we have 3x times 6x cubed divided by 3x is 2x squared. Remember the exponent rules from the last module. Minus 9x squared divided by 3x is 3x, plus 12x divided by 3x is 4. We have now successfully factored the polynomial by factoring out the greatest common factor. Let's try another example. 14x cubed y plus 7x squared y minus 7xy. Again, we start with the numerical coefficients, then we're going to use our shortcut for the variables. 14 is 2 times 7. 7 is its own prime factorization. So for each of the 7s, we just say 7 represents its prime factorization. When we look at all three coefficients, they have a 7 in common. So our GCF will equal 7 times. And when we look at the x's and the y's, the largest exponent of x is 1, and that shows up in the last term. The largest exponent of y is 1, and that shows up in every term. And so our variable will be x, y. So our GCF is 7xy. At this point, we rewrite our polynomial as a product of the GCF 7xy times, we're going to divide each term by 7xy to figure out what the resulting polynomial should be. So we have 14x cubed y over 7xy plus 7x squared y over 7xy minus 7xy over 7xy. So this becomes 7xy times, and let's divide each term. 14 divided by 7 is 2, x cubed divided by x is x squared, and y divided by y, those cancel. Plus 7 divided by 7 is 1, so we don't have to write it because we have variables. X squared divided by x is x, and y divided by y cancels. Minus. The 7's cancel, the x's cancel, and the y's cancel, so we put our placeholder of 1. When everything cancels, it becomes 1 when we are multiplying and dividing. Let's now try an example where the greatest common factor is not a monomial. In this case, we have 6 times the binomial x plus 2 minus y times the binomial x plus 2. If we were to write the prime factorization here to find the greatest common factor, 6 is the same as 2 times 3, and we also have a factor of x plus 2. The x plus 2 is attached together. We can't say that's an x and a 2. It's just x plus 2. When we look at the second term, y times x plus 2, its prime factorization would just be y times the factor x plus 2. And so in this case, we would say that the first term and the second term have an x plus 2 in common. Anytime we are rewriting a polynomial, we write the greatest common factor first, which in this case would be x plus 2, times the resulting polynomial. We find that by taking the original terms and dividing them by the GCF. Now, if we thought of this x plus 2 in each division as just an x, we know what happens if we have x in the numerator and x in the denominator. They just cancel. Well, the same thing with x plus 2. So in our first division, x plus 2 in the numerator, x plus 2 in the denominator that cancel. We're left with 6 minus, again, the x plus 2's cancel, and we're left with a y. So now we have successfully factored our polynomial. Let's try another example. We can look and tell pretty quickly that the x, y, and the negative 1 in front of each binomial have nothing in common. And so our greatest common factor again, and so instead of writing each prime factorization, we can skip straight to the fact that the greatest common factor is y plus 1. Once we find the greatest common factor, we write it on the outside of parentheses. We then write each original term being divided by that greatest common factor. And then we divide. So we have y plus 1 times, the y plus 1's cancel in the first term, and we're left with xy. When the y plus 1's cancel in the second term, if the whole thing cancels, we're left with a minus 1. It'd be just like if we had 5 divided by 5. When the numerator and denominator are the same, that equals 1. Let's now look at factoring by grouping. This is a special factoring method that when we have 4 terms or more than that. We first group the terms into 2 groups so that each group has a common factor. Step 2, we factor out the GCF from each group, and then step 3, if there's a common binomial factor, and hopefully there is, we factor that out as well. And so every time we factor by grouping, we're looking for 3 greatest common factors. Let's try an example. So we want to factor 15x cubed minus x minus 4 by grouping. So the first step is to create 2 groups. I'm going to underline my first 2 terms and underline my second 2 terms. It is possible to rearrange your terms before you start, but it's not always necessary. If we look at the first 2 terms, we have 15x cubed minus 10x squared. And after we do a bit of work, we can find that the GCF between those 2 terms is 5x squared. Once we find the GCF, we're going to write it on the outside of the parentheses, just like we did on the previous problems, and then we're going to write the resulting polynomial. Because you're really good at factoring out the greatest common factor now, I'm going to skip every intermediate step. You can do that on your own, pause the video if you need to. And so we divide. 15x cubed divided by 5x squared is 3x, minus 10x squared divided by 5x squared is 2. So we finished factoring our first of 3 greatest common factors. Now, it doesn't matter to me what the third sign is, positive or negative. I'm always going to write a plus here before we write the second greatest common factor. Now we look at the 6x minus 4, and we would do some work, find the prime factorization if you need to get the GCF equals 2. So we write the 2 on the outside of parentheses. We divide each original term by that 2. 6x divided by 2 is 3x, minus 4 divided by 2 is 2. We've now factored out the second greatest common factor. So our third greatest common factor is 3x minus 2. So just like we did in the last 2 steps, we write that greatest common factor on the outside, and we now divide each term from the previous step by 3x minus 2. Then the binomials cancel, 5x squared for the first term, plus the binomials cancel, and we're left with a 2. And we've now successfully factored by grouping.